Heat capacities of an ideal gas. Recall that there are 2 molar heat capacities for an ideal gas. We will just call it the heat capacity. CV is the heat capacity at constant volume, so dQV equals NCV dt is the heat added at constant volume for temperature change dt, and dQp equals NCP dt is the heat added at constant pressure, where Cp is the heat capacity at constant pressure. At constant volume, since dV equals 0, the work dW equals pdV equals 0. The first law is du equals dQ minus dW, so at constant volume dQV equals NCV dt, which is equal to du. At constant pressure, work dW equals pdV is done, so dQp equals NCP dt equals du plus pdV. Since u is a function of T only, du is the same for a temperature change dt regardless of the process. Therefore, du is the same for a temperature change at constant volume and at constant pressure, so it is the same in the 2 expressions. We see that the heat Qp at constant pressure is larger than dQV at constant volume for the same change dt. Let's just consider an increase in T. For positive dt, energy must be added to increase U. At constant volume, the heat dQV adds the required energy, but at constant pressure there is an expansion, so some energy is lost as work pdV done by the gas. To compensate for this loss, extra energy must be added in addition to the du needed, so dQp must be larger than dQV. Let's look at these 2 steps on a PV diagram. Suppose that the gas starts at an initial state on isotherm at temperature T and increases its temperature by dt to a state on isotherm T plus dt. The constant volume step is a small isocore upwards during which dQV is added to increase the internal energy by du, where dQV equals du equals NCV dt. All the heat is converted to du. The constant pressure step is a small isobar to the right, during which dQp is added to supply both the energy lost by work pdV being done and expanding, and the energy for du. It doesn't matter what path the gas takes from T to T plus dt. The internal energy increase du will be the same because U depends only on T. du is thus the same for the constant volume and the constant pressure step. What is different is the work done and hence the heat that must be added. Since du is the same for any step, we can use the constant volume step to find for any step, including a step at constant pressure, that du equals NCV dt. We now derive an important relationship between CV and Cp of an ideal gas. From the ideal gas law, PV equals nRT, for P equals constant, a change on both sides of the equation is dPV equals dnRT. Now dPV equals pdV since P is constant, and dnRT equals nR dt since nR is constant, so pdV equals nR dt. Now pdV equals dW, and this is a process at constant pressure, so we may write dWp equals nR dt. We know that dQp equals NCP dt, which is equal to du plus pdV. We also know that du equals NCV dt for any process, including this one at constant pressure, so we can substitute it for du and substitute nR dt for pdV to obtain NCP dt equals NCV dt plus nR dt. Dividing through by n dt, we obtain the final result, that Cp equals Cv plus R. This is a most useful result, for once we have found Cv, we just add R to find Cp. Recall that a monatomic ideal gas has U equals 3/2 nRT. So du equals 3/2 nR dt, which is equal to NCV dt. So CV equals 3/2 R. So a monatomic ideal gas has Cp equals 3/2 R plus R, which is equal to 5/2 R. A diatomic ideal gas has U equals 5/2 nRT, so du equals 5/2 nR dt, which is equal to NCV dt, and Cv equals 5/2 R. Hence, a diatomic ideal gas has Cp equals 5/2 R plus R, which is equal to 7/2 R. To conclude, a useful property of an ideal gas is the ratio gamma equals Cp divided by Cv. For a monatomic ideal gas, it is gamma equals 5/2 R divided by 3/2 R, which is equal to 5/3. And for a diatomic ideal gas, it is gamma equals 7/2 R divided by 5/2 R, which is equal to 7 divided by 5. So the ratio of heat capacities are, for a monatomic ideal gas, gamma equals 5/3, and for a diatomic ideal gas, gamma equals 7/5.